All right, hi everybody. We're going to be going over some of the topics that are covered in the homework, specifically stuff with esters. And esters are going to look generally like this. So we can see here, this is very similar to a carboxylic acid, but instead of having an OH group right here, we have that OR. And all that means is we have an oxygen attached to a carbon chain. That carbon chain can look like anything. In this case, I just made it a propyl. But we can see here that this is sort of a combination of an ether plus that carboxylic acid, which I'm just going to call Ca. And so we have this name here that we're just going to call it an ester, which is sort of like carboxylic acid plus ether together makes an ester. All right. Okay. And so we're going to be talking about esters overall today. But before we do that, I kind of want to talk about just this carbonyl group right here. And a carbonyl group is just whenever we have a carbon double bonded to an oxygen. All right. So let's look at this C double bond O. And let's compare this to something like C bound to a Cl. So oxygen and chlorine, they're both more electronegative than carbon. So they're both going to get a partial negative charge, whereas the carbon is going to get a partial positive charge. And whenever we had something like this, something with a carbon attached to a chlorine, we could subject that to a substitution reaction because this carbon here is slightly positive, so it's going to attract nucleophiles. So like if we had an example of that here, we would have this chlorine being partially negative, this carbon being partially positive. We have a nucleophile, which is going to come over. It's going to attack this right here. This bond is going to leave, and we just end up with, oops, wrong color. We just end up with an SM2 reaction, which basically means we replace that Cl with a nucleophile. Okay. And so we can see here that similar to this CCl bond, this C double bond O bond is going to react in a similar fashion. So we have C double bond oxygen and then two groups next to it. Those two groups can be anything, including the ester. We'll get to why the OR, the ester group, is different in a little bit. But first, let's just talk about what's going to happen in this case. So of course, we're going to have our nucleophile. And our nucleophile is going to attack the partially positive carbon, and we are going to have something that's similar to a leaving group. So one of these oxygen bonds right here is going to sort of act as a leaving group. So we still end up losing a bond, but it's not as if we're losing a whole atom. So instead, we end up with carbon here, oxygen with a negative charge because it just lost one of its bonds, my nucleophile right here, and then my two other groups right here. Sorry if you can hear my dog, he's freaking out. Don't know why, but he's a good boy. Anyways, so we end up with our oxygen here and our nucleophile here. So the identity of these two groups here, I'm going to call them group A and group B, that's sort of going to determine the next step. If A or B are good leaving groups, then we'll have to do something else. But for right now, let's avoid that. And let's just say A and B are not good leaving groups, so nothing is going to change. The only thing that's going to occur is we are going to expose this to an acid, which will end up protonating this oxygen. And we sort of end up with an alcohol group right here. So if we don't have any good leaving groups, this is simply the mechanism, okay? And that's it. So let's do like just a quick example of this. I'm gonna go ahead and delete this one right here, just so I have a little bit of room. So let's do a quick example. So let's say that we have something like this. Carbon and hydrogen are both bad leaving groups. And I have two carbons right here, and that means that we have zero good leaving groups. We'll get into that in a second. So let's say that we have a nucleophile, and let's say we have a specific nucleophile called a Grignard's reagent. A Grignard's reagent basically means we have an R group, aka a carbon, that is ionically bound to a magnesium, which is bound to any halogen. So chlorine, bromine, those two are the most common ones. So let's just use a chlorine right here. So we have our R group right here, which is just going to be a carbon, and then MgCl right here, which is going to be just sort of the positive portion of this. And so what we see here is something that's sort of similar to when we talked about nucleophilic atoms or nucleophilic molecules that have a metal attached to it. So if we have NaOH, we should know at this point that we're going to rewrite this as Na plus and OH minus. This is the same thing here, where the MgCl is sort of like going to be our Na plus, and then our carbon group will be our OH minus. All right. So let's go ahead and just make up some sort of carbon group. Let's say that it's an isopropyl group, and it looks like this. So in problems, a lot of the times, you'll see it drawn like this. But what it's really sort of showing, or what it's really sort of representing, is something like this, where we redraw it as the nucleophile and sort of the positively charged portion as separate. It's sort of like how you see NaOH the same in the same place, so like NaOH like this, but we know that it's going to decompose or disassociate into Na plus OH minus. It's the same thing here. Anyways. And so this is called Grignard's reagent. And the way that I remember what Grignard's reagent is it has an M and a G in it, and Grignard starts with a G. So it's like, oh, Grignard's, Mg, magnesium. Oh, it makes sense. It's a little silly, but I find that remembering silly stuff can help you remember really hard stuff. All right, so back to this. So now we have our nucleophile, which is gonna be this carbon portion right here. It's going to attack the partially positive carbon attached to the oxygen. This bond is going to break in order to make room for that as the leaving group. And then we end up with sort of like a cross here, where this carbon here in the center is going to be where that partial positive charge used to be. So one of these groups is going to be O negative. One of the groups is going to be the new nucleophile, which is the isopropyl group right here. And then these other two groups are going to be the rest of the molecule. And this is where I'm going to recommend that you start numbering things. So like I number this 1, 2, 3, 4. So I know that this center carbon here is going to be 3. So one of these carbon or one of these offshoots here is going to be 4. So it's done. So like this one, I'm going to say this is going to be 4. And then the other offshoot is going to have 2 and 1. So we can see here is 2 and here is 1. So we can see that, let me get a different color. Our original carbon chain right here is right here in this cross. Okay? All right. And so now we're going to say, do I have any good leaving groups? And as I said before, carbon is a horrendous leaving group. So no, we don't have any good leaving groups here. So what we're going to do is we're going to take H plus, and that's essentially going to be created by an acid, whether it be H3O plus, H2SO4, or just water can also provide an H plus because water has a certain number of H plus and OH minus, et cetera, et cetera. But all you really need to see is a hydrogen, and what's going to happen is the oxygen will grab onto the hydrogen. That will cause it to protonate, and we end up with this final sort of structure right here. And I'm going to look at this, and I'm going to say, okay, this structure doesn't really look how we would usually draw it. So what I'm going to recommend that you do is find the longest carbon chain and make that sort of your parent chain. So in this case, it'd be 1, 2, 3, 4, 5. So let's number that. 1, 2, 3, 4, 5. Let's redraw that. 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. We know that there's an OH group on 3. We also know that there's a methyl group on 3. And then we know that there's a methyl group on 4. So this would look more like an answer that you would give on like a final test, or if you have multiple choice. The actual answer is going to look more like this than like this. All I'm saying is that drawing this cross is going to help you keep things straight a lot more than if you tried to continually draw it like this. All right, so I'm going to encourage you to draw this cross and then redraw it as what the answer is going to be drawn as usually. Okay? All right, so that's if you do not have a good leaving group. But what if you do have a good leaving group? So let's erase some of this stuff right here. And like we said before, we're going to treat OR as a good leaving group. So we're going to say, what if instead of having this methyl group right here, we have an OR right here? So let me erase this up here just so I have a little bit of room. So we're still going to be using our Grignard's reagent, and we're still going to use that exact same first step. Okay? So the exact same first step, we end up with O negative here, our new nucleophile right here, and then just our methyl group right here. So 1, 2, 3, and then our OR group right here. All right. So if you recall, the next step, if we did not have a good leaving group, was to protonate this oxygen right here. Instead of doing that, what we're going to do is we are going to have the leaving group leave and allow this oxygen to recreate its double bond. So we end up with something that looks like this, where all we've done is we basically replace this OR with this isopropyl group, okay? So that is the first step. We still have a second step to go through because the Grignard's reagent is really, really powerful. And so what's going to happen next is we're going to say, oh, we can see here we still have this partially negative oxygen and this partially positive carbon. So we're going to take our same Grignard's reagent and we are going to react again. We're just going to be doing this exact same reaction that we did before where we didn't have a good leaving group. So like, for example, if we use this same reaction here, we're going to say, okay, we're going to have that exact same Grignard's reagent. Oh, my dog's saying hi. We're going to have the exact same Grignard's reagent, do the exact same mechanism where we attack that center carbon, we make our cross, where this is going to be our center carbon, and we're going to number things because I love numbering things. So 1, 2, 3, 4, 5, 6. So we're going to say, okay, 1, 2, 3, 4, 5, 6. And so then there is our original chain. Then we're going to have an oxygen right here, negatively charged oxygen. And then we're going to have our nucleophile right here, which again is just that isopropyl group. And then we just finish it off like we did before. We'll have H plus be grabbed by this oxygen, and we end up with our final alcohol right here. Again, this looks kind of weird, so we're probably going to redraw this. So we have our quote unquote parent chain. So like 1, 2, 3, 4, 5. Or you could draw it a different way where you made this our beginning or this our beginning. Just as long as you're sort of choosing a parent chain to act as sort of the quote unquote parent chain, you'll be fine because it'll be a lot easier to figure out the answer if it's drawn in a familiar way. So, sorry, I have to change from my highlighter. So we say 1, 2, 3, 4, 5. And so it's going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. We know 3 has an OH group along with that isopropyl group. We know that 4 has a methyl group, and then there is our final answer. Okay? So we can see here, when we have an ester, we are going to add our nucleophile twice, essentially, and get rid of the OR group, okay? That is the base mechanism for what we're going to continue to do. All right, I'm going to go ahead and clear the screen. Oh, go ahead.
Yes, so for the textbook, it uses CH3, CH2, MGBR. Is that the same as the Grignard?
Yes, this would be sort of the same thing. So you said CH3, CH2, MGBR. So this would be also a Grignard's reagent, but instead of having an isopropyl group, this is just an ethyl group for the Grignard's reagent. So like this group right here is what you're actually adding. That's what's actually acting as your nucleophile. So if I were to draw this in the stick model, it would look kind of like this.
Okay.
Okay, does that
And
answer
how
your
would
question?
it work? Yeah, and how would it work if you have like a ring with multiple
Yes,
oxygen?
I'm about to do that one. Exactly. We're gonna
Okay.
go into a ring because I think that is probably the hardest question that you can
Mm-hmm.
ask as far as this process goes. So I'm gonna go ahead
Okay,
and
thank
clear my
you.
screen. Quickly take a screenshot if you need to, but yeah. Okay. So what if, like you said, we have sort of a ring here instead of just a linear form. So what we can do is we can say, all right, so the R group, quote unquote, is going to be this whole thing right here. And so what I'm going to do is I'm going to redraw this so it looks like just a linear figure. So I'm going to say, okay, 1, 2, 3, 4, 5, 6. So I'm going to say oxygen is going to be my 1, 2, 3, 4, 5, 6. And my double bond is right here. But what's important to note is that there is a bond between this oxygen, oxygen number 1, and then carbon number 6. So now we can see sort of a more familiar representation of this circular, this cyclic compound. And so let me swap it a little bit so that I have my O group on this side. So I'm just going to sort of erase this right here and this right here. Oops, that's what I meant to do. I'm going to erase this here. I'll put the oxygen right here. So this is going to be 1. And then we're going to have a bond between 1 and 2. Okay, so now we can see that ester group, that OR group, a lot better. So let's say that we're using the same Grignard's reagent. We're just using this isopropyl group with MgBr, MgCl, same thing. And then what's going to happen is same thing as before. Our Grignard is going to attack that partially positive carbon. This bond is going to break, and we're going to end up with sort of like this right here. We're going to have oxygen negative right here. We're going to have our new nucleophile right here. We're going to have oxygen right here. And then we're going to try and draw this as a cyclic. I'm awful at drawing this portion, so bear with me. So this is going to be 1, 2, 3, 4, 5, 6. So you can see here, we still have our cyclic right here. But what we can also see is we've added our Grignard's reagent. Okay, and so now we know that when we have that OR group, it's going to act as a good leaving group. It's going to leave, and we are going to recreate that oxygen double bond. And so what'll happen is we basically are going to end up with 1, 2, 3, 4, 5, 6. We're going to end up with this. So we can see here that essentially what we did is we replaced this oxygen here. We cut off this bond. We replaced it with this bond right here to the isopropyl group. And that sort of swings the oxygen over to this side right here. And we end up with 1, 2, 3, 4, 5, 6. Okay. And I know we didn't mention it before because it didn't really come up, but it sort of assumed that when we protonate this oxygen right here later, this one will become protonated. Okay. So right now this is negatively charged, but the next part is we are going to have our Grignard's reagent react again. I'm going to draw that up here. GBR. And essentially what's going to happen is it is going to grab here. We end up with, oh dear, 1, 2, 3, 4, 5, 6. O negative here, 2 isopropyl groups here. And then we end this with protonation, where we protonate both this oxygen here and then this oxygen here. And so we end up with a diol, where we have 2 OH groups. We're sort of a dialcohol, so we're going to call it a diol. Okay, so that's how you do this question when you have multiple, or when you have it in a ring form. All right, does that make sense to everybody?
Would the final product be open or would it still be a ring?
This final product, it would be open. It would look, this is the final product here.
Oh, okay.
After,
And like you said earlier, with the CH3, like with the ethyl, uh,
yes,
would it look instead of the isopropyl, it would have the ethyl?
yes, exactly. So if we had the ethyl group, it would look more like this.
Okay,
Okay,
thank you.
no problem. And one last thing to mention, this MGBR, this group right here, this is a very, very powerful nucleophile. So if you have any oxygens in your little guy here, if you have any oxygens, it's gonna try and react with them. So like, for example, if I have a carbon chain that looks like this, and I have a double bond right here, I have an OH right here, and then I have another double bond right here, my Grignard's reagent is going to react with every single one of these. It's going to replace the oxygen. It's going to turn this into an alcohol. It's also going to turn this into an alcohol. Sometimes you want to avoid that. So sometimes what you'll see is something called a protecting group. Okay? So like if for example, I wanted to somehow, let's say I had a BR right here, and I wanted to transform this into a Grignard's reagent. Let's get rid of these and these. Let's say I have an alcohol group and a BR group, and I want to turn this into a Grignard's reagent. If I just had the BR, all I would have to do is react this with Mg in ether, specifically ether because that's a non-polar solvent. That will just essentially shove the Mg between the BR and we end up with our Grignards. However, the Mg is also going to be attracted to the oxygen. So to avoid reaction with the oxygen here, what we're going to want to do is protect it. We're going to use a protecting group. And so most of the time that protecting group for our cases is going to be CH3 SiCl. And so what this group is basically going to do is it's going to take this hydrogen here on this oxygen and it's going to replace it. And it's essentially going to replace that hydrogen group with that Si, this is a 3-methyl group, so I'm going to say Me3 here, okay? And so what that essentially does is it sort of prevents the Br, or it prevents the Mg from attacking that oxygen. So it's forced to make the Grignard's reagent with the bromine. And so then we end up with this right here. I hope I'm using the right number of carbons, but one can hope. I'm just going off of what I've seen. Again, if you're doing this for you, I would recommend numbering it and making sure you're using the right number of carbons. But I want to get through all these different topics here. Okay? And so after this, we're going to want to get rid of this protecting group right here. And to get rid of this protecting group, we're going to use basically a special reagent called TBAF. All right? One more thing. A lot of the times after you make this here, after you make this Grignard's reagent, you're going to react it with our carbonyl first before you use our deprotecting, okay? So 99% of the time, if you have to protect something, your first step will be to protect, and then your last step will be to deprotect with TBAF, okay? So 90% of the time, 99% of the time, that's what you're going to have to do. You're going to protect first and then deprotect last. So like, for example, if a question has a step before this one, before the TBAF step, that is fine. It's just you deprotect last. Okay, I just sort of skipped that portion just to show you the deprotecting part. And so then we end up with our Grignard's reagent with its regular OH group right here, and that's how you deprotect. Okay? Does anybody have any questions about that? All right. No? Awesome.
You mentioned that there could be a step before you deprotect. Would you just add like a carbonyl group? Like I'm looking at an example right now and it has like adding a carbonyl. So could you
basically
just like,
what would happen is we would use this as our Grignard's first, before we deprotect. So like if I had my carbonyl here, what would happen essentially is we would add this to our carbonyl, this would leave, we would turn it into an alcohol, and then we would deprotect. So it's like you use this as a reagent before you deprotect because you deprotect last. Okay?
Yes, thank you.
Does that answer your question?
Yes.
Okay, awesome. Okay, so that was the big portion that I wanted to cover during this whole session here. But we can also go over some naming stuff. So let's just quickly do this name here. So we'll just do this, our OH group right here, and then this right here. Okay, so to name this, of course, first you're going to want to find the parent chain. So that'd be this one right here, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you're going to want to number the parent chain, giving the substituents the lowest number possible. So obviously, it would number from this side, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you're going to say, okay, my base name is going to be non-name. And you know what? I'm going to add something really quickly. I'm going to add a double bond right here. Okay? So our base name is going to be non-name. And I see, okay, I have an OH group right here and a double bond right here. Both of those will change the actual parent name. So, oops, let me highlight that in a different color, in blue. So if I wanted to change it using the double bond, I would call it non-ene. So you see here, I sort of changed the AN to an EN. If I wanted to name it using the alcohol, I would name it non and all. So you can see here, I changed the E for the alcohol. So in order to name this for both the alkene and the alcohol, you're basically going to smash these together into non, ene, all. So you can see here, that's where we get that final name from. You're just smashing together what you already have into our final name. So that means our parent chain, or our last sort of parent name here, is going to be non-enol. All right. And so, of course, we're going to have to number this. So we're going to have alcohol is going to be on carbon 2. And our alkene is going to be on carbon 4. Remember, you start numbering, or you give the alkene the number that it starts on and not the number it ends on. There are multiple ways that you can sort of name this. You can either say non 4 ene to all, which I prefer. I prefer this way. Technically, you could also name this for non-ene to all, but you can't really put both of these numbers in front of the non name, because that would make things confusing, and it makes it really hard to tell which one is going to be 4 and which one is going to be 2. So again, I prefer this way, so I'm going to go ahead and use this as my parent name. So my parent name now is going to be non-4-ene to all. And so the last part here is going to be adding that last substituent right here. So the first thing I'm going to do is I'm going to say, okay, this is a weirdly shaped substituent. So I can't exactly say propanol, or like I can't say it's a propyl group or a butyl group or whatever. I have to find out that special name. And so I'm going to say here, okay, this group here, this has 4 carbons. That means overall, we're going to be calling it a butyl group. However, it's in that sort of chicken leg shape. So that means we're going to be calling it isobutyl. So we're going to have 3 isobutyl non-4-ene to all. And one last thing, if we had, if for example, we had our stereochemistry right here, like let's say it was a solid wedge right here, we would have to also give the actual R or S configuration. So in this case, let's do this sort of together. So obviously, all of these carbons right here are going to have the same priority. So we have to go the next bond. Obviously, we can see here that this group on the left has the higher priority bond overall. So we're going to call that group on the left group 1, as it's going to be the higher priority. We're going to say, okay, now we're sort of duking it out between these two groups. We can say, okay, both of them have a carbon attached to, this carbon is attached to another carbon. However, this one up here is attached to a carbon twice, which we're sort of going to count as 2 carbon bonds. So overall, this top one is going to be a higher priority. So this is going to be priority 2. This will be priority 3. And again, priority 4 is kind of like a hidden hydrogen back here. And since priority 4 is on the dashed wedge, we don't have to do anything with this. And so we're going to say, okay, 1, 2, 3. This is clockwise. So we're going to say this is going to be R-3 isobutyl non-4-ene 2-ol. All right. And that's how you would name this guy right here. Any questions about that? All right. All right, awesome. So the last topic I want to cover today has to do with lithium aluminum hydride. Okay, so lithium aluminum hydride, the main, the main thing about lithium aluminum hydride is it gives off a lot of hydrogens. It donates a lot of hydrogens to everything it can. And what's important to note about these hydrogens is these hydrogens tend to be negatively charged, which makes them into nucleophiles, very strong nucleophiles. So for example, if we have something that looks like this, the hydrogen will attack here, this bond will leave, we end up with our little cross right here, and then we protonate, and then we basically end up with an OH group right here. This overall is going to be called a reduction. So you've probably heard of oxidation reduction before in chemistry, Gen Chem, whatever, and you probably have definitions for them in your mind. But the way that we define oxidation and reduction in organic chemistry is slightly different from how you would have defined it before. So if you remember, in Gen Chem, oxidation is loss and reduction is the gain of electrons. So I'm going to say gain electrons. And then I'm going to put oxidation over here, and we're going to say it's the loss of electrons. But in organic chemistry, the way that we're going to say this is reduction is the gain of carbon hydrogen bonds or the loss of carbon X bonds, where X can be an oxygen or it can be a halogen. Whereas oxidation in this class is going to be the loss of carbon hydrogen bonds or the gain of carbon X bonds. And the reason why, so I'm going to go ahead and erase this right here just so I can sort of show this. And the reason why we call reduction the gain of carbon hydrogen bonds is because what happens here? So if I go from, like, let's say a carbon oxygen bond to a carbon hydrogen bond, when we had that carbon oxygen bond, the carbon was slightly positive and the oxygen was slightly negative. But when we go to a carbon hydrogen bond, that carbon is, for all intents and purposes, neutral, which means that overall it had to have gained some negative charge. It had to have gained some electron density in order to become neutral. So when we gain carbon hydrogen bonds, that carbon essentially gains an electric charge, or a negative charge. My cats are growling at each other. It essentially gains a negative charge, which means it's gaining electrons. And the same idea here. When we lost this carbon-oxygen bond, that carbon became neutrally charged. So we gained electron density for that carbon. It's the exact opposite over here. If we are going from a carbon-hydrogen bond to, carbon-oxygen bond, again, will be going from a carbon bond that is effectively neutral to a carbon bond that is slightly positive. So that carbon had to have lost electron density, which means that would have been oxidation. So when you hear me say reduction is the gain of hydrogen bonds or oxidation is the loss of hydrogen bonds, know that I'm using the organic chemistry definition, but also know that it kind of also works with our gain electron, loss of electron definition. So I digress. Lithium aluminum hydride is what we would call a strong reducing agent. So what it's going to do, it's going to add a bunch of hydrogens wherever it is possible, okay? So like for example, if we took that ketone that we had before, oh, this carbon here, this carbon has a double bond to an oxygen. One of those double bonds can be lost and we can end up with an OH group and a new carbon hydrogen bond, which means that we have reduced, okay? What's also important to note is that we aren't going to lose this sigma bond right here. All we're really able to lose is that pi bond, okay? All right. In another case, if we have a carboxylic acid, this is going to reduce it all the way to just a regular alcohol. It's basically going to get rid of this oxygen overall. And this is because of the this is because of when we talked about before, whenever we had a double bond oxygen, that carbon there is going to be partially positive, and if we have a good leaving group right here where OH in a carboxylic acid, as far as when we're talking about lithium aluminum hydride can go, we consider that a good leaving group when reacting with lithium aluminum hydride. So essentially what's going to happen is it's going to react once and replace that OH with an H group, and then it will react again. Oh, sorry, that should be an H, not an OH group. Sorry, I just drew the same carboxylic acid. And then it will react again and turn this oxygen into an OH group using the same exact mechanism that we saw before when we had an ester. Okay? All right. All right, so lithium aluminum hydride, if we have multiple sort of oxygen groups in the same vicinity, in the same molecule, if we react with lithium aluminum hydride, all of these will be reduced all of the way. So this carboxylic acid will just simply become an OH group. And then this ketone group will also become an OH group, and et cetera, et cetera. We can see how that reacting with just lithium aluminum hydride will reduce all of these to their most reduced forms, making sure that we don't break any sigma bonds. All right. Does that make sense to everybody?
I have a question.
Go ahead.
If it's an ester, how would it be reduced?
It would be reduced in the same way, like for example, let's say that we had the cyclic ester once again. It would be reduced in the same way before that we add the Grignard's reagent. So for example, what would happen is this ester would break, this ester bond would break, and we end up with 1, 2, 3, 4, 5, 6. We'd end up with 1, 2, 3, 4, 5, 6. We would have a double bond here when the ester bond breaks. But once we actually reduce everything, this will also become an OH bond. This is an OH bond. Okay? Does that make sense to everybody? Does that answer your question?
Yes, thank you.
Okay, awesome. All right, and I think we're about out of time for today. But if anybody has any last minute questions, feel free to ask them. Otherwise, I hope everybody here has a great day, and I'll see you next time.